Section 2.1 is entitled Inductive Reasoning. Inductive reasoning is a different way of dissecting a problem so that you can figure out a pattern. So let's first just start with an example. So number 1, describe how to sketch the fourth figure in the pattern. So we can see here that figure 1 starts off with 2 boxes, figure 2 starts off with 4 boxes, and figure 3 starts off with 8 boxes. So each successive box has twice as many boxes, or has been split up into twice as many boxes as the previous one. So to draw the fourth figure in the pattern, the square would have to be divided into 16 smaller rectangles. We also have some shading going on. If you notice, the figure number 1 has the first box is shaded, and figure number 2, the first box is shaded, and figure number 3, the first box is shaded. So when I draw the fourth figure, not only is it going to be split up into 16 equal-sized rectangles, I'm also going to continue that shading pattern by alternating the shaded regions. So to sum it up here, each large region has twice as many equal regions as the previous figure, as we stated before. So to sketch the fourth figure, you would start by dividing a square into 16 equal-sized vertical rectangles and then shade alternate regions, starting with the first rectangle being shaded. Next in our path of discovering what inductive reasoning is, let's look at example number 2. Describe the pattern in the numbers 1,000, 500, 250, 125, ... and write the next 3 numbers in the pattern. Now remember that the ... means so on and so forth, so you're going to continue that pattern in the same way as the previous numbers. So the problem first wants us to describe what the pattern is. I noticed that each number in the pattern is 1/2 of the previous number. So 500 was half of 1,000, 250 was half of 500, and 125 was half of 250. So again, each number in the pattern is 1/2 of the previous number. Next, they want us to write the next 3 numbers in the pattern. So to continue the pattern, we just have to take half of 125, and then half of that number, and then half of that number. So half of 125 is 62.5. Half of 62.5 is 31.25, and then half of 31.25 is 15.625. Next, let's see some vocabulary. So a conjecture is an unproven statement that is based on observations. So thinking back to the previous 2 problems, we saw patterns in the situations that we were given. For example, in the first problem, we saw that each additional box was split up into twice as many boxes as the previous one, and the shaded regions were alternating. In the last problem, we saw that each new number was half of the previous number. So again, we were finding patterns based on the observations we were getting from the situations we were given. So basically, when we came up with those patterns and stated what we found, those were conjectures. And that's exactly what inductive reasoning is. Inductive reasoning is when you find a pattern in specific cases and then write a conjecture. So again, that's exactly what we were doing in the previous 2 problems. We analyzed the situation, figured out what the pattern was, and then came up with a conjecture based on that pattern. So again, we were just using inductive reasoning. And just to restate, the one thing you can take away from this is inductive reasoning is just figuring out a pattern and then writing down what that pattern is. I'd write that down in my notes. Let's see some more examples of using inductive reasoning. So example number 3, describe the pattern in the numbers 1, 2.5, 4, 5.5, ... and write the next 3 numbers in the pattern. So when I look at this pattern, I see that each new number is 1.5 more than the previous number. So my conjecture would be each number in the pattern is 1.5 more than the previous number. And then to find the next 3 numbers, I'm just going to take the last number, 5.5, and add 1.5 to it. So 5.5 plus 1.5 is 7. 7 plus 1.5 is 8.5. And 8.5 plus 1.5 is 10. So again, I'm using inductive reasoning to figure out these patterns and to state my conjecture. Example number 4 gives us a broader example of using inductive reasoning. It says, make and test a conjecture about the sign of the product of any 4 negative numbers. So not only are we supposed to come up with a conjecture based on the pattern that we see, but we're also supposed to test it, meaning actually show problems in which our conjecture is working out. So let's just first look at, what if I took a negative times a negative times a negative times a negative. It doesn't really even matter what those numbers are, it just matters that they're negative. So think about what a negative times a negative. A negative times a negative is a positive, and then times a negative again would be another negative, and then times another negative would change it back to positive. So a negative times a negative times a negative times a negative is a positive. So let's state our conjecture. The product of any four negative numbers is positive. Now let's test this out. If I take any four negative numbers, so let's take -1 times -2 times -3 times -4. -1 times -2 is 2, times -3 is -6, and then times -4 again would be positive 24. Let's just try the same number times itself 4 times. So -2 times -2 times -2 times -2. So -2 times -2 is positive 4, times -2 again is -8, times -2 again would be positive 16. So not only did we just make our conjecture, but we also tested it with a couple examples. Again, let's jump into some vocabulary. To show that a conjecture is true, you must show that it is true for all cases. However, if you want to show that a conjecture is false, you just need to find one counterexample. So a counterexample is a specific case for which a conjecture is false. And just to reiterate, if you want to prove that a conjecture is true, it needs to be shown that it is true for all cases. But to prove that a conjecture is false, you only need to come up with one and only one. Even if there's more than one, you only need to show one time that the conjecture is false by providing a counterexample. So let's see some examples of that. Example number 5, find two counterexamples for each conjecture. So here's the first one, part A. The conjecture is the difference of any two numbers is always smaller than the larger number. So first we need to think about what all these words mean. The difference means to subtract. So the difference of any two numbers is always smaller than the larger number. We need to find two examples where this is false. My mind immediately goes to negatives. If I take a number like 10 and subtract -3 from it, I would end up getting positive 13. This conjecture said that the difference, so I subtracted, of any two numbers, 10 and -3, is always smaller than the larger number. The larger number in this case is 10, and it's saying that that difference, 13, is always going to be smaller than the bigger number. But in this case, I got 13, which is bigger than 10. Let's look at another example. If I take -7 minus -4, I get -3. The bigger number here is -4. -4 is actually bigger than -7. But when I subtracted the two, I got -3, which was actually bigger than -4 since it's closer to 0 on the number line. So here again, I found an example where the difference of any two numbers is actually bigger than the larger number, thus disproving this conjecture. Part B, the conjecture. The quotient of two numbers is always smaller than the dividend. So quotient means to divide, the answer to a division problem. And dividend is actually the number that's being divided. So if I'm taking 10 divided by 2, 10 is the dividend, 2 is the divisor. So let's find at least two examples where this is false. My mind goes to fractions because I know weird things happen when I divide with fractions. So let's just start off with, just like last time, 10. And I want to divide by 1/2. If you remember, dividing by a fraction is the same thing as multiplying by the reciprocal. So the reciprocal of 1/2 is 2. So 10 divided by 1/2 is the same thing as 10 times 2, which would give me 20, which would disprove this conjecture that your answer is always going to be smaller than the dividend. So 20 was bigger than the dividend of 10. Let's look at another one. Let's see if we take something like 15 and divide by 1/3. So here again, dividing by a fraction is the same thing as multiplying by the reciprocal. So 15 divided by 1/3 is the same thing as 15 times 3. So I end up with 45. Again, disproving this conjecture that your answer is always going to be smaller than the number that you started with. As always, make sure you jot down any questions or comments you have about these notes so that we can cover them in class.